Bismillahirrahmanirrahim. Today I wanted to do some examples about the material that we talked about last time. Last time we talked about the interior angles, the sum of the interior angles of a polygon. So if I were to draw a pentagon here again, it's an awkward looking pentagon, it's a bit of artistic work here, but if I were to add up all the interior angles here of this particular polygon, they would be the sum of all the interior angles. And the way you can find the sum of all of the interior angles of a polygon were these two particular formulas in this particular theorem that we talked about last time. And I suggest that you can do that using two separate formulas. That's this one and this one. And I also suggested to you last time that I actually don't memorize these per se, because if you understand the concept of how one gets these formulas, then it becomes very easy to derive them once you understand them. And I said one way of doing it is you can divide this polygon. You can divide any polygon into triangles, and we understand that the sum of all of the interior angles of a triangle, they all add up to 180 degrees. So all the interior angles of a triangle add up to 180 degrees, and if you were to take the interior angles of these two triangles like this, and if you were to add them up, and that will give you the sum of all of the interior angles of the polygon. So all of these added together, and this one plus this one plus this one plus this one, and you can see that's the sum of the interior angles of this particular polygon. So you can divide a polygon into its constituent triangles, so to speak, into its the number of triangles that you can make inside, and you can find the sum of the interior angles like thus. So if you have a pentagon right here, and you can take any vertex and you start cutting the pentagon into the smaller triangles, and you can see if it's a five-sided polygon like over here, you can cut it into three triangles, divide it into three triangles. That's because from any particular vertex, you can make a diagonal to other vertices, except you can't make a diagonal from to neighboring vertices like this one. So that's no diagonal, that's just a side. So the number of triangles that you can make from in a particular triangle from any particular vertex will be always 2 less than the number of sides. So 2 less than the number of sides. So whatever the sides is, if it's a pentagon, that number of sides is 5, of course. 2 less than that would be the number of triangles that you can make out of that particular polygon. And then you just simply multiply that by 180 degrees, because each triangle is 180 degrees. So one way of finding out the total, the sum of the interior angles of a polygon would be to subtract 2 from the total, the number of sides of a triangle, and that the 2 from the size of a polygon, and that will give you the number of triangles you can make, and multiply that by 180 degrees, and that would give you the sum of the interior angles of that polygon. And I suggest that another way of doing that is, instead of dividing up triangles like that, you can take the polygon, and whichever polygon you're dealing with, and you can imagine a point somewhere in the middle of this, and from that particular point you can make triangles out of it like this. And you'll notice the number of triangles you make will be equal to the number of sides the triangle has. That kind of funky looking segments there. Maybe I could try to do a little bit better job. So if you any point, imaginary point, and from there you could draw little segments there and cut this like a slices of pizza over here into different pieces. So if it's a 5-sided polygon, you can construct 5 triangles. Okay, 5 triangles. If it's a 6-sided polygon, you can construct 6 triangles like this. So and then if you were to add up all of these angles, all right, plus you would have to also add up, because each triangle is 180 degrees, right? So you add up all of these as well. But these center angles right here are not part of the polygon, so you have to subtract those angle measurements away. So but all the center ones will always add up to 360 degrees. So with whatever, however the number of sides the polygon has, that's how many triangles you can construct, and then you multiply that by 180 degrees. But then you have to subtract the central angle, which is 360 degrees. So the second way would be to start with the point in the center and create triangles, and the number of triangles you can create will be the same as the number of sides, n times 180 degrees. So the sum of all of the angles will be n times 180 degrees, but then you would have to subtract these inside these angles over here, because those angles are not part of the polygon, and so you would have to take away from it 360 degrees, because they add up to 360 because it's a nice circle. So these are the two formulas, and I suggested I don't memorize these because they're so intuitive and so beautiful, and once you understand it, it's easy to derive. So the way you calculate the sum of the interior angles of a polygon is by these two formulas: n minus 2 times 180 degrees, and or n times 180 minus 360 degrees, and where n being the number of sides of the polygons. So today I wanted to use this theorem and do some examples, so we have some practice. So here's example number 1. So this example says, find the sum of the measures of the interior angle of a convex hexagon. Now, this particular question also reminds me to tell you that this method is only for convex polygons. So if you remember, there are two types of polygons, concave and convex. Convex are polygons that we're dealing with here. Concave are polygons that kind of have a dent in this. So like this would be a concave polygon where it has a little dent inside. So you can't apply this to concave polygons. So anyways, so that's particular the importance of this particular adjective. Now, the sum of the measured interior angles of a heptagon. Heptagon is 7-sided polygon. If you have 7-sided polygons, you can make 5 triangles out of it, right? Because, you know, you draw them lines, if you remember. So it's 5 triangles, so you subtract 2 of the 5 times 180 degrees, okay? So 7, heptagon is 7. 7 minus 2 is 5. So 5 times 180 degrees. Now, you can do this in a calculator, or you can do mental math, because if you do this 10 times 180, that's 1800. Well, you want half of that. 1800, that's 900, right? So that's going to be 900. So in other words, what I did here is mental math. So 5 times 180 degrees is 10 times 180 degrees. That's twice as much, and divided by 2. Because 10 times anything is easy, that's 1800. And you divide by 2, that's 9 times 18, so that's 900. So anyways, the answer is 900 degrees. So the sum of the interior angles of a convex heptagon is 900 degrees. So that was easy enough. Let's see what we have next. Now this question says, find the measure of each interior angle of a quadrilateral ABCD. So here's a quadrilateral ABCD. Notice quadrilaterals or polygons very easy to name. You can just name the polygons using the vertices. Vertices are labeled using capital letters because they're points, and then you just trace out in the clockwise or counterclockwise in any particular starting at any particular vertex. So the same polygon could also be named B, C, D, A, and that would be the same polygon. Different ways of naming triangles, different ways of naming polygons. Anyway, so here the question says, find the measure of each interior angle of a quadrilateral ABCD. So we are supposed to basically find the measure of this and this. How do we do that? Well, we're given that these are 90 degrees. Those are right angles. Those are simple right angles. That's good. And we're given some variables. So here's a question that presumably requires us to do some algebra. Okay, so, well, the sum of the interior angles of a quadrilateral, okay, because then you can make 2 triangles out of a quadrilateral, right? That's 360 degrees. Okay, that's easy enough, right? Because quadrilateral is 4 sides. 4 minus 2 times 180 degrees. That's 2 times 180. That's 360 degrees. So the sum of the interior angles of a quadrilateral is 360 degrees. And they already told us this is 90 and 90, right? So that's 180. So these two must add up to 180. In other words, if you take all of these angles, that's 3x plus x, and then you added the 290 degrees, that's 90 plus 90, that should add up to give you a total of 360 degrees, right? Because that's the sum of all the interior angles of a quadrilateral. Pay attention now. So that's 4x plus the 180 degrees equals 360 degrees. Subtract that, so 4x is going to be equal to 180 degrees. Subtract 180 degrees from both sides, and then you divide both sides by 4, and this is going to be 45. Okay, so that's x is 45. So this angle is going to be 45 degrees, but we were asked to find all of them, find the measure of each interior angle. So we're not done yet because we have to find this. So 3 times x is going to be 135, right? Because 45 to 90, 90 and 135. So this 3 times x is going to be 3 times 45, and that's going to be 135 degrees. And ta-da, there we have it. So we have all of the angles of this particular quadrilateral. Okay, so let's see what question comes our way next. It looks like we're going to be doing more algebra. So example number 3, find the measure of each interior angle of a pentagon HJKLM shown. So HJKLM, notice they went in order. You know, you just don't pick up any vertices and label them, but you go in order. HJKLM, pentagon, and we're supposed to find the measure of each interior angle. Well, we're getting the idea now. This is algebra, so we're supposed to, first we have to find out the sum of all of the interior angles of a pentagon. Well, by now we're pretty expert at it. So it's a pentagon, so it's 5 sides. You can make, you have to subtract 2. You can make 3 triangles out of this. So 3 times 180 degrees, and that we have already discovered. That's like 540 degrees. So the sum of all the interior angles of a pentagon, as we said, is 540 degrees. Okay, so we got that. Now, so n minus 2 times 180 degrees. Well, there's the other way of doing that. Remember, if you have a pentagon, if you were to draw like from the center right here, you can make 5 triangles out of it, right? So another way of doing the same problem is you can make 5 triangles from, if you imagine imaginary point in the center, and that's 180 degrees. But then you have to subtract 360 from it. That's point all the angles in the middle, and this again will come out to be 540 degrees. Anyway, so we found out the sum of all of the interior angles of this pentagon, and then we're supposed to find out these angles specific measures. Now we're going to use algebra again. So all of these will add up to 540. Okay, so I have 142. Okay, that's degrees, plus 2x plus 2x. I see it looks like 4x. I hope you follow me because I'm just adding these up. And I'm 2x plus 2x is 4x. And I notice these two are also the same. Okay, that's 2 of them, right? So that's 3. I mean, let me just not rush this. Maybe you get confused if I rush it. So there's 2 of them, 3x plus 14. I hope you're not confused about this because there's 2 of them. I just added them together. Okay, so that, and then this is supposed to be 540 degrees like that. Okay, so let me just do this. 142 degrees plus 4x plus, I'm going to add these two. That's 6x plus 14 plus 14, that's 28, and that's supposed to be 540 degrees. All right, so, and then that's 4x plus 6x, that's 10x plus 28, so this is 40, 150, 60, 70, that's 170. I hope I'm doing the math right. Equals 540 degrees. Okay, so 10x plus 450, 60, 70. Okay, I'm going to subtract 170 from both sides like this. So 10x is going to equal to, so that's going to be 70, that's 30, is 200, 300, 400, 500, and 40, that's 360. Is that right? So that's 360. I hope I'm doing this. So the x is going to be equal to 36. That's x. Okay. Now the x is 36. Okay, mind you, x is 36, but that's not in the answer to the question. Let me just use 540 minus 1. I'm just double checking my math because I did make a mistake. I hope you caught that if you're paying attention. I was just checking to see. 540 minus 170. So 540 minus 170. You better check my math. That's 370, mind you. That's 370. I did make a mistake here. So that's 3 70. As I said, it's always remember, it's always important to get the question right than to look cool. So divide both sides by 10, you get 37. I hope I did that math right. Okay. Now double check this, make sure I don't fall my. So x is this. So 37 times 2, 74. So 2 times x. Okay, this ends up being 2 times x. If you calculator, that's going to be 74 degrees. Ta-da! That's that. So this is the same here, 74 degrees. We got that. And here 3 times x. That's 3 times 37 plus 14. Okay. So let me do that. So 37 times 3 equals that, plus 14 equals 125. That's 125 degrees. Okay, and that's 125 degrees because this is the same. Both angles are the same. So there it is. That's how you solve this particular question. Now, you always have to be careful with the math. You don't make silly mistakes like I did over here. So I hope I didn't make any mistakes here, because you know sometimes it's hard to talk and do the math at the same time. All right. So anyways, I hope I did that correct. Let's see if I have another question to finish off today. Okay, so here it is. So find the measure of each interior angle of a regular hexagon. This one is slightly different, but it's not difficult, I don't think. So first we have to understand the meaning of the regular hexagon. So if you have a hexagon, it's a 6-sided polygon. Let me draw one out. 1 and 2, 3, 4, 5, 6. So this is a 6-sided polygon. That's a funky looking 6-sided polygon, but that's a hexagon. Okay, but it's not a regular hexagon. A regular hexagon would be one where all the sides are congruent and all the interior angles would be congruent. So that's the definition of a regular polygon, if you remember. A regular polygon is a polygon where all the sides are congruent and all the interior angles are congruent. So that's the definition of a regular polygon. In this case, a regular hexagon. All the sides are congruent, all the interior angles are congruent. So this is no ordinary hexagon, it's a regular hexagon. That is, it's a 6-sided polygon where it's like this. Okay, well, my picture's not the best, but all the sides are congruent. So let me draw all the sides are congruent. And all the interior angles are congruent. So if you find one interior angle, basically you find all of them. So these are all congruent. Okay, so that's a regular hexagon. So you're supposed to find the measure of each one of them. So if you found one, you can find all of them, and that's going to be easy enough because you can find the sum of all of the interior angles. The sum of the interior angles of a hexagon is going to be 6 minus 2. That's the number of triangles you can make. 6 minus 2 times 180 degrees. Correct? So the sum of a hexagon, this ends up being 720 degrees according to here. So that's 4 times so that's 4 times 180 degrees, and that's 360 times 2, that's 720. Okay, so now that's one way. The other way of doing that, of course, is if you have a hexagon, you can make 6 triangles out of this. Remember, like that. So that would be 6 triangles, but then you have to subtract 360 degrees. That's the inside circle thing. So that's also 720 degrees. Anyways, that's the sum of the interior angles. If the sum of the interior angles of a hexagon is 720, and if this is a regular hexagon, all you have to do is you have to divide the 720, the sum, and divide it by 2, and then you would get divided by 6. That's 6 angles, right? So, and we give you each individual. So 720 divided by 6. And that will give you each individual angle. And that's going to be, so each of them is going to be 720 divided by 6, and that's going to be 120 degrees. there you have it. So divided by 6, and that's 120 degrees. So each one of these is 120 degrees. Now this is only for regular polygons, of course, where all the interior angles are congruent like this, and that's how you were able to find the measure of each interior angle, because they all happen to be the same. If they were not same, then it would be, if they were not same, it would be this problem, because that's not a regular pentagon. And a regular pentagon, all the interior angles would be congruent. So the way you find this, each interior angle of a regular polygon, you find the sum and divide by the number of angles, because all the angles are congruent. Inshallah, we shall develop on these concepts next time. Until then, As-salatu was-salamu ala rasulillah walhamdulillahi rabbil alameen. Assalamu alaikum.